Hey everyone, it's AthenaX. For this video, we're going to step away from probability and MLE for a bit. We're going to revisit the best fit line problem, but this time choose a different but still reasonable loss function to optimize. As a reminder, the setup is the following. You have a bunch of XY samples and you want to find the line that best fits this data. For a potential line, the residual is the difference between the actual y and the predicted y on the line. Earlier, we chose the sum of the squares of the residuals as a measure of how poorly a line fit the data. Then we minimized this sum of squares. This approach is called ordinary least squares, or OLS. So far, so good. But choosing to square the residuals probably felt a bit arbitrary. When I first approached this problem many years ago, I probably would have just taken the absolute value of the residuals. So that's what we're going to do in this video. We'll be minimizing the sum of the absolute values of the residuals instead of the sum of the squares of the residual. I think this approach goes by many names. Upon some Googling, it seems the common name is Least Absolute Deviations, or LAD. We'll call it that, but the name isn't important. So let's try to find the solution for this. Now, if the function was differentiable with respect to the betas, we could take the partial derivatives, set them to 0, and solve. But the problem is that this function is not differentiable with respect to the betas, since the absolute value is not differentiable. So we need to find some other way to solve this. You might say, okay, well, the absolute value is differentiable everywhere except for one point, right? Except at x equals 0, it's differentiable everywhere. So if we can find which side of the point we're on, maybe we could differentiate it there. It's a good idea. You'd have to do it for every single absolute value though, so we have n different absolute values here. So as far as I can tell, it's not feasible to do this. You don't know for each of these which side of the y-axis here you're going to be on. It turns out there is a whole class of optimization problems called linear programs, which we know how to solve efficiently. However, these solutions are not given in closed form, meaning there isn't a formula for the solution. That may seem funky, but it's the truth. It turns out that we can express the LAD regression problem as a linear program, and then solve it using one of the linear program solvers. In the next video, I'll go over the definition of a linear program and how we can express LAD regression as a linear program.